All right, it is Tuesday. Yeah, it is Tuesday. Tuesday, April 28th. Let's go ahead and continue our review series. This is review number 7, the second part of electrostatics. All right, so we kind of went overboard yesterday, overtime, skipped out on the Q&A session. So we'll try to do a little less today to average the 2 days out. Isn't that the day before it's due? Yes, I didn't open. I mean, if you're done, you're done. That's good. I didn't open the submission thing yet. So once it's open, and then I will mention it. I can open it, but I just won't talk about it. Anyway, it will be titled Video Challenge 1. So look for that. How do we show our work? What? Okay, video challenge 1. Video challenge 1. So you are to submit a video. So video should have front view of the entire thing. Entire run. And clips used for video analysis. Now, remember, you're not analyzing the entire run. You're only analyzing the final shot and the first bounce or whatever it is, and then the final bounce. Clips used for video analysis. Okay, and you're also submitting a document, so PDF. And the PDF should contain everything else. So what is everything else? Well, start with like a purpose statement. Describe the setup. So this would include like your materials, and perhaps even if people have helped you, if you received help from family members, so include them. Include assistance. So if you did it with Granny or whoever's at home, and then yeah, make sure you give them credit. Yeah, it's challenge 1 because what else are we gonna do? Just more and more challenges, but different kinds. It's not all just frame by frame video analysis of everything. And then the rest of the PDF document should have all the date, like the data and calculations I talked about on go viral on TikTok. Yeah, that's the challenge. And then make sure you get me sponsored or something by some company. That's challenge number 3. Get Mr. Z sponsored by NVIDIA. And then the analysis. All right. Try to do MP4 video. So MP4. I guess AVI also works. Is it called AVI? I think it's called AVI. So MP4 or AVI. What does your phone record as? Typically, most phones do MP4, I think. But if you want to process your video, like the run video on like Adobe Premiere or something, feel free. You can use H.264 codecs, and and all that stuff, and then save it as an MP4. All right, so let us continue. This is Electrostatics II. So we did the, well, we were looking at the inside, outside of shells, so let's continue with that topic. So if I had a shell, I don't like that one. That's a little better. So if I had a shell, no, I don't like this at all. Let's see if I can move it. That's a little, yeah, there we go. So let's say the shell itself is positively charged, and it has charge of Q. I shouldn't do arrows. Let's say this is charge capital Q, and then inside we place, directly at the center, we place a negative little q. Like so. Okay. Now, of course, you know, the overall charge, if I am outside of this hollow shell, or this is a hollow spherical shell, if I'm outside of this shell, the total charge is equal to Q minus Q. Okay, so that is the total no matter what. Now, depending on the type of material, different things can happen. It should be only at the start, like if it's the first time you log into Twitch, then you get one, probably like 15 seconds or something. I mean, I guess you can block it. Yeah, I'm not really a partner yet. I think you need like 75 average viewer count to hit partner, and I'm literally at like 7. We have less and less people, so there's no way we can hit partner. When you refresh, let's see, well, get like a Chrome extension or something. Yeah, get a Chrome extension. All right, so insulating material. Now, to have an insulating material charged up evenly like this is a challenge of its own. And so, but assuming that we have a even distribution of volumetric charge, this volumetric charge density will remain as is for the most part. For insulating materials, we could always polarize the atoms. For insulating material, we can polarize the atom. So we can shift around. So if I can zoom in here, so let's say we have a tiny little atom here, and by placing this, oh my gosh, ink to shape, whatever, this little tiny atom, so by placing this negative charge inside there, it will shift. Ooh, whoa! It'll shift the electron to one side, to the right side, and this makes the left side a bit more positive. Okay, but if I had a conductive material, conductive, or metal, if this was metal, charges will shift and they will actually move around. So instead of this just singular atom changing the internal structure of itself, okay, we're going to pull charges inwards such that the positive charges start lining up closer to the inner wall. And thus this makes the outer wall negatively charged. Okay, so how much charge gets pulled in? Well, about Q amounts, and that would make this negative Q amount, or I should say Q. I dropped Q. Oops. We started with Q, didn't we? Oh, I have two Qs. No. All right. So what is the inner lining? Well, the overall needs to be capital Q, but we will shift it. We will shift positive Q worth of charge here, and negative Q worth of charge there. Does the circle rod thing have to be charged for the Q minus Q inner outer wall thing to happen? Yes. Well, no, I shouldn't say charge. It has to be conductive. So it doesn't have to be technically. Here, let's do it this way. So let's say the outer shell. Oh, that didn't work. It's just negative Q here. And this will pull in positive charges from the neutral shell. So shell is neutral. And this would mean that the overall is positive Q. This is minus Q. If I'm outside, this is minus Q plus Q minus Q, which is just minus Q. If I'm outside, total is negative Q. Oh, ink to shape, go away. Total equals negative Q. Total equals a negative Q. Okay. Now if I do inner Gaussian surfaces, so if I'm like right here, my total enclosed is 0. And then as I expand out, I'm getting more and more negative until I hit the outer edge. And then I have, I'm back to negative Q. Here it's slightly different. We actually have a charge. Okay. Now I want to pull in some charge. I'm going to pull in positive Q worth of charge. So what is left is Q minus Q. So this is Q plus Q, Q minus Q, and then we have negative Q. So here we have negative Q plus Q plus Q plus Q minus Q. Wait, this gives us 2Q. Nope, nope. Q plus Q minus why is it 0 if Q minus Q is enclosed? So all the capital Q goes to the surface. Wouldn't it be plus Q inside and Q minus Q? I tried to use black and pink. I guess that's where I messed up. So the black is supposed to be here. And then the pink should be here. Yep. So now if I did this, if I do it in order, the green is the inside. So let's color code this. There. So the green is the inside, negative Q, and then plus the pink, and plus the black. There. And this gives us Q minus Q. Yay, color code. With voltage, or I should say electric potential, remember you can use superposition for electric potential. Let's say you are at this spot inside. So we'll just use the neutral example. Or you could use the other example, it doesn't matter. You should be able to do both. You can use superposition where you do, the voltage from the inner voltage from the inside. So this is green. Okay, and then voltage from pink, and then voltage from the outer black, right? What else? So we did Gaussian cylinder, Gaussian sphere, and the last one is the pill. Gaussian pill. If you have a sheet or a box plane of charge, there we go. And I want to know the electric field. Well, I need to capture all of the electric field that is coming out. And because it's an infinite plane, we can ignore the sides. So we use two sheets. Two sheets. That doesn't look right. how can I draw this underneath? Let's see. Maybe closer in. Hmm. Let's try a different method. Okay, and then we'll place this inside. There. Now it makes sense, right? So the black one is in between. I haven't practiced my art skills. I guess I can make it dashed here to represent that. That one is below. Alright, so the pill has two areas, A, and nothing in between. So we're going to do the sandwich, the Gaussian sandwich model. And if I do flux is equal to the closed loop integral of E dot dA, it is equal to, on the right side, Q enclosed over epsilon naught. Whoa, why am I pulling that up? Q enclosed over epsilon naught. So again, you factor out the E, and then you get integral of dA. Integral of dA is the area, but you have two of them. Let me write it this way. Okay, you have two of them. So I'll write 2 times whatever the area is. And so the electric field at some distance above this plane, and if I had this plane, we're just some distance above. Okay, so of course the positive charge would mean that there are vectors every which way. But ultimately the x components cancel out, and it doesn't really matter where. It doesn't technically have to be at the center, because the plane is really huge in comparison to our dot. So we have Q enclosed over 2 times A times epsilon naught. Okay. So what we do is we rewrite it. We have Q, which is charge, divided by area. Charge per area is charge density, surface charge density. And so that is eta over 2 epsilon naught, or 1/2. Okay, then we put them next to each other, so we make 2 of them. We do it by connecting them to some sort of potential difference, a nice potential difference of of epsilon. This is epsilon naught, the permittivity of free space. What is epsilon naught equal to? Epsilon naught permittivity of free space, it's equal to 1 over 4 pi times k, Coulomb's constant k, 9 times 10 to the negative 9. And this is how we create our parallel plate capacitors. And we know that the electric field goes from the positive side to the negative side, and it's a uniform electric field. Okay. Now, what is it equal to? Well, based on the fact that we have Gauss's law, we can do 2 pills, and so we would do 2 pills for each. Now, assuming that the areas are the same, if the areas are the same, then the electric field is 2 times the electric field in a plane, which is 2 times 1/2 eta over epsilon naught, which is just eta over epsilon naught. This looks like mu, doesn't it? There we go. 8 over epsilon naught. But of course you can still use VED. Where D is the gap or the distance between the plates. Now your traditional one only has air as its dielectric, and then we can change the material, the peanut butter and the jelly in our sandwich here, in our parallel plate sandwich, to change the amount of stored charge. Because how come the electric field isn't dependent on the radius? Because it's really big. It's at the plate. Yeah, it is. I mean, it's at the plate, but it is above. But the height itself is negligible in comparison to the length of the width, I should say, x. And this is x. Yeah. Remember, our Gauss's laws are kind of like the extreme cases only. It's a very simplified, it's a simplified model, right? Gauss's law is a simplified model based on, geometry and symmetry, and ultimately it's at the extreme cases of your integrals. So we saw that we can do integrals for a rod and then a plane and all that yesterday, and you saw that the actual equation is a little bit more complex. But if we let certain things, reach infinity, or or say that something is negligible in comparison to some other dimension, then we can finesse the equation and make it a bit more simpler. And for all intents and purposes, it's close enough to where it doesn't really matter. Technically, you could do a double integral. So if you want, if you're in multivariable calculus, go ahead. So multi-kids, okay, see if you can do this. It's a lot harder than you think. But imagine this being your dq. Your dq is now based on area, so it's eta times dx dy. And so if you are some distance above, then you have to find r, etc., how far you are, and then find every single electric field component that comes from every single dq, every piece of area. Okay. And ideally you can ignore all the x components and then just focus on all the y components. Okay. No, no, it's each electric field is the electric field line is at a particular point, right? And it comes from every single DQ that is available. So for example, this little charge would be giving you that electric field. Here, let's use different colors. This green part gives you that one. The black one gives you this one. Right. And doing a double integral with dx dy is quite challenging. If you did the ring, the rings are a little easier because you can do polar coordinates. And then you transition into a disk. You can find the E of a ring first, and then change R as R goes from 0 to capital R or something like that. Or I should say R to R. Yeah, it radiates from every little charge, and then you're adding all the vectors at that exact point only. Right, so let me use a different color. Man, that math test really destroyed. I think Sword Hero is the one who said it. The math test destroyed your brains today. All right, back to these capacitor stuff. Let's see, where do we actually talk about capacitor? Capacitors. Oh, right here. Capacitors. So I guess we'll intro to capacitors, and then we'll call it a day. Yeah, I'll just write it here. Capacitors. This was a side question. Q equals CV. Remember, capacitance C is measured in what unit? How do you measure capacitance? Chat, how do you measure capacitance? Farads, F. Capital F, capital F. So by combining the VED equation and this equation, we were able to find the capacitor equation itself, right? So VED tells you that V is equal to ED, which is now equal to Q over C, capital C, not lowercase c. And then rewrite C, the capacitance, is equal to Q divided by ED, like so. And then replace E, the electric field, inside the capacitors. We get Q is equal to, C is equal to Q divided by, E is actually eta over epsilon naught, now times D, the distance between the gap distance. And then rewrite eta. So we get Q divided by, eta is charge per area, and Q's cancel, leaving you with A times epsilon naught over D. So that's the relationship between the area of your metal plates and D, the gap. Q is the charge on one plate, or the magnitude of it. Charge on one plate. And remember, the overall charge is actually, it's 0, because one plate is positive Q, the other plate is negative Q. So overall, it's actually 0. But we only measure the charge that is held on one side. Right? What do we do with dielectric? Well, dielectrics, we can place some jelly, some insulating material. And how does it change? Well, then C becomes some kappa times A epsilon naught over D. Okay, similar to your if you're doing AP2 and you're learning about light, and you have index of refractions, kappa is kind of like an index of refraction. Okay, and you can use 1 for air, kind of like the index of refraction of air is 1. Aru? What is Aru? Oh, Yupperoo. Yes, very good. So with different materials, you can have higher values. So that means by putting these dielectrics in between, what we do is we change the ability of the capacitor to hold extra charge. Yep. So the capacitor is able to hold extra charge. And this is where the actual design of the capacitors comes from, in that you have your two sheets. They're very long, kind of like, imagine two unrolled sheets of toilet paper or paper towel, like so. Okay, and then at the end you connect it to a little wire, pew, and then two little prongs like so. In between, you put your dielectric material, your insulating material, so the two things cannot touch. Okay, and last but not least, you roll it. So this is almost like making cannolis, or it's a Danish. If you've ever baked, you'll see that it creates a little spiral formation. Whoa! So inside this spiral, we have two black lines. Let's see. This doesn't look right at all. Let's try again. There we go. And in between the black lines, we have our dielectric material. It's our capacitor Danish. Oh, I'm hungry. And so when you roll it up, what does it look like? Well, it looks like a cylinder. And those two little metal things that we have here are the little two legs that stick out. And you can't see the rest because it's covered in black tape or insulating tape. Plastic, I should say. Insulating plastic. Okay. All right. I think we covered electrostatics. Of course, we skipped all of AP1 electrostatics, so everything about, electric force vectors, adding vectors, figuring out where you have zero electric force and all that stuff is, right? Here, let's do a quick example before we end it. Let's say we have two charges. Right? One is plus, and it's some sort of plus Q, and the other is minus, and it's minus Q. So there we have it. We have two charges. Okay. Where is the electric field, the strength of the electric field, the greatest? Is it A, somewhere over here? Actually, I don't want to give you options. No, I should. Let's see. Options: A, B, C. C is directly in the middle. D, E. Is it any of these? Is it a combination, or is it none of the above, or is it cannot be determined? So it's not just a singular letter that is the option here. Is it a combination? Is it a oh, it could be a singular. Some of you think it's singular. Or could it be none of the above? Or could it be cannot be determined? No. Because if you are super close to a charge, it's infinite. Yeah, that is true. That is true. All right, let me explain why one of the answers is not correct. And the one that is not correct is C. Right? So you might be thinking, wait a minute, how could it not be C? Right? The electric field points to the right from the plus end. It points to the right, or it's away from the positive, and it is towards the negative. So the electric field add up, and etc. etc. So it should be maximized in the middle, but not necessarily. It's because B and D are close. Yeah, B and D are close. So let me use a FET simulator, our very favorite. There we go. And don't forget about these simulators. They're good. You might be thinking, oh yeah, that was totally AP1 only. So let's use the charges and fields here. Okay, I'm going to turn on the grid values. We'll put just a one charge here at this this junction here, this grid, and then let's use 1, 2, 3. There we go, 1, 2, 3. Of course, these vectors are showing you the electric field lines, right? And we can use this meter to measure the. Oops, this is potential. That's not what I want. I want the sensor. We want the sensor to measure the electric field. It's going to measure the electric field in volts per meter. And you can see how in the middle, we actually have a minimum, somewhere around 17.6 volts per meter. And then if I get closer, we start increasing. Whoa. And then as I move towards the blue, we increase. Whoa. C is actually the opposite. Yikes. Yikes-a-rooney. Not yupperoo. Noperoo. So yeah, definitely choose the ones that are close. Close is definitely better. Right? And the last thing, the last topic we did was the equal potential lines. Whoa, what happened? There we go. The equal potential line. Yeah, luckily there won't be any MC questions. The equal potential lines are perpendicular to the electric field lines. I wonder if I still have it. Let's see. APC, E&M. Uh-oh, I don't think I have it. Oh well, I'll just draw it. Let's just do a simple model. Here's plus, and then these are equal potential. What is equal potential? Chat, define what an equal potential line is. These contour rings, these concentric circles. Okay. It has equal potential. Yeah, it's any point on this circle has the same potential value of, in this case, this equation only works for point-like particles, right? Of course, you can have more complex shapes by putting in multiple charges. Your equal potential lines could look different, and so this leads us to a different simulator called the electric field hockey. Where is it? Hockey. There it is, electric field hockey. Now you do need Java for this, so you know, I'm sure. Hopefully it's not a virus. It's definitely a virus. No. Where is it? Oh, it opened as a WinRAR. I don't want to use WinRAR to open it. Oops. Use Java. Here it is. And so by using multiple charges, we can control. Let's see. We can control. Whoa, that was loud. We can control how the charges will flow. The field lines will tell you which way the object will accelerate. WinRAR 40-day trial forever. Let's go to a harder one. Challenge 2. Oh gosh, that's way too hard. All right, this is a little easier. You can reset, clear. Now I want it to be repelled and then bounce off. How do I do this? Oh gosh, that was a fail. Reset. Maybe I want more thrust. More repulsion. Is that right? Oh my gosh. Are you serious? Are you serious? Maximum efficiency. Yes. What? What happened? No. Minus. Reset. Oh wow. Okay, well, you guys can try this on your own. You will need Java runtime environment. It is an older simulation kit. Unfortunately, there's no rage quit. I didn't rage quit. I hit the clear button on accident, and we're running out of time. So anyway, as I was saying, the equal potential lines can be more complex, right? But pay attention to the line density. And so wherever so these are the equal potential lines. Of course, the electric field line would be going from high to low. So this is like 10 volts. This is 5. This is 0. It's -5. And so it would be perpendicular. I'm going to go this way. Okay, not only that, not only is it 90 degrees to each equal potential lines, these are volts, 10. We can also map the strength of the electric field. Here in this field, the electric field is not constant everywhere. It depends on how it is changing. Of course, if I say this is E1 and I want to compare it to E2, E2 being over here, how would they compare? Okay, chat, here's your final question. E1, here's this box. E2, is it greater than, is it, oh, that's less than, is it less than, greater than, equal, etc. We got a greater. Oh, interesting. If whatever the answer is, go ahead and leave it in the comments below. Thanks for tuning in. I'll see you next time.